Lesson 7.6 is double and half angle formulas. So double angle formulas are when you have a 2 theta inside of your trig function. So sine of 2 theta is equal to 2 sine theta cosine theta. This comes directly from our sum formula. So 2 theta is the same thing as theta plus theta. So if I apply the sine sum formula, same sine opposite trig function, I get sine theta times cosine theta plus cosine theta times sine theta, which is 2 sine theta cosine theta. And then similarly, cosine 2 theta is equal to cosine squared theta minus sine squared theta. Again, directly from our sum formula for cosine. Cosine of theta plus theta, same trig function, opposite sign. Cosine theta times cosine theta minus sine theta times sine theta. Therefore, cosine squared minus sine squared. Cosine 2 theta actually has 3 identities. If you apply the Pythagorean identity, sine squared plus cosine squared equals 1, you can replace the cosine squared with a 1 minus sine squared. Minus sine squared, you end up with a 1 minus 2 sine squared theta. Or you could replace the sine squared theta with a 1 minus cosine squared theta. So you get cosine squared minus the quantity 1 minus cosine squared, which is 2 cosine squared theta minus 1. So there's actually 3 identities for cosine 2 theta. It's helpful to know all 3 of them. If you don't memorize all 3 of them, at least memorize the first one, the original, and then know how to derive the other 2. And then tangent 2 theta is 2 tangent theta over 1 minus tangent squared theta. Again, derived directly from the tangent sum formula. But again, you could always do sine divided by cosine if you really needed tangent. The half angle formulas are if you're dividing the angle theta by 2. So sine of theta over 2 is equal to plus or minus the square root of 1 minus cosine theta over 2. Cosine is a plus instead of a minus in the numerator, and then tangent of theta over 2 is plus or minus the square root of 1 minus cosine theta over 1 plus cosine theta. It's not actually plus or minus in the sense that you get 2 answers. It's plus or minus in the sense that you have to figure out whether you want the positive answer or the negative answer. So you have to figure out what quadrant your original angle theta was in, and therefore what quadrant theta over 2 would be in, so half of that angle, and therefore what your trig function is going to be, whether it's going to be positive or negative in that quadrant. So here we have the cosine of alpha is equal to negative 3 over 5, where alpha is between pi and 3 pi over 2. And we want to evaluate these angle sine of 2 alpha, cosine of alpha over 2, and cosine of 2 alpha. So this is very similar to what we were doing in the 7.5 with the sum and difference formulas, and all the way back in chapter 6 with just the regular trig functions. So go ahead and pause the video and try these. So what I did is I started by drawing my triangle in the 3rd quadrant because it indicated that alpha was between pi and 3 pi over 2. Cosine is x over r, so negative 3 is my x, 5 is my r, which means 3, 4, 5 right triangle, and negative 4 is my y. So then sine of 2 alpha is 2 sine alpha cosine alpha. I don't know what alpha is, but I know that the sine of alpha is negative 4 over 5, and I know the cosine of alpha is negative 3 over 5. So I multiplied all this together, and I got that sine 2 alpha is 24 over 25. For cosine of alpha over 2, it's plus or minus the square root of 1 plus cosine of alpha over 2, where cosine of alpha is negative 3/5. So I end up with 2/5 in the numerator divided by 2. I end up with plus or minus the square root of 1/5, or plus or minus 1 over root 5, or plus or minus root 5 over 5. Those are all equivalent. So then I had to figure out whether it's going to be positive or negative. The original angle is in quadrant 3. It's between pi and 3 pi over 2. So if I cut that in half, I cut my whole interval in half, alpha over 2 is going to be somewhere between pi over 2 and 3 pi over 4, which is in the 2nd quadrant. And cosine of alpha is negative in the 2nd quadrant, so therefore I want the negative solution, so negative root 5 over 5. Cosine of 2 alpha, you can use any of the 3. A lot of times if I'm doing this, I would pick the one that only had cosine in it, the 2 cosine squared minus 1, since I'm given cosine. In this case, I've already found sine, so it doesn't matter, but I use the cosine squared of alpha minus the sine squared of alpha, where cosine of alpha is negative 3/5, sine of alpha is negative 4/5. I squared them, subtracted, and get negative 7 over 25. So now we have more identities, more formulas. Just like we talked about in 7.5, we could now use these to establish identities. We could also use these to help us solve equations. So for example, I have cosine of 2 theta equals 2 minus 3 sine of theta for 0 is less than or equal to theta is less than 2 pi. It's okay to have 2 theta in an equation if you don't have any other thetas in there. But in this equation, I have both a 2 theta and a regular theta, so I need them all to match. So I want to use my double angle formula to make it so that I only have regular thetas in this trig function or this trig equation. I notice that I also have a sine here, so I'm going to have everything be in terms of sine. So I have cosine of 2 theta is equal to 1 minus 2 sine squared theta. So I replaced cosine of 2 theta with the 1 minus 2 sine squared theta. So now everything is just a regular theta inside the trig function, and everything is only in terms of sine. And now this looks like one of the ones we've done previously where it's a quadratic and I can solve it the way I solve quadratics. So solving this like a quadratic, I moved everything over to one side. I got 2 sine squared theta minus 3 sine theta plus 1 is equal to 0. And then I factored. It factors into 2 sine theta minus 1 times sine theta minus 1 equals 0. Zero product property, 2 sine theta minus 1 equals 0, which means sine of theta is equal to 1/2. So therefore theta is pi over 6 or 5 pi over 6. Or sine of theta minus 1 equals 0, which means sine of theta equals 1 or theta equals pi over 2. So we can't have a 2 theta and a regular theta in the same equation, and we can't have different trig functions in the same equation. So I utilize my double angle formula to make all of that match.